Am I audible to all of you?
Yes, ma'am.
Okay, so Austin, Faiza, Humam, Tarif, and Chavez. All right, this is the last topic from this lesson, current electricity. See, combination of resistors we had seen, combination of capacitors also we had seen. Now, if we say combination of identical cells, when I say combination of identical cells, that means all the cells are having the same value of EMF. That is what is meant when I say identical cells. So now combination of identical cells means if I have connected n number of cells, let's say 1, 2, 3, 4, 5, many cells I have connected. All are having the same value. Even if one is different, we won't use the formula. Which formula we'll use, that I'll tell you later. But for identical cells, because these cells have to be identical, first point is fine, they have to be identical. Now see, how do you calculate the series and parallel connection? Series and parallel connection identification again remains the same. Now see, here along the cell, we will have the internal resistance of the cell also, right? The particular internal resistance of the cell also we will have. So you will calculate equivalent resistance the way you have been calculating. That is not difficult task. Equivalent EMF, I'll tell you. See, if all the cells are connected, you have E plus E plus E plus E. These are the number of cells which are connected. Directly add all the cells. The way we add in series combination, all the resistors we have R1 plus R2 plus R3 plus R4 plus R5 like this. So if you have n number of cells connected, just keep on adding them. E plus E plus E plus E like this. This becomes E plus E plus E up to what? All the number of E's which are possible. So let's say if I say n number of cells are connected. So what will be the EMF? NE. For example, if I say 3 cells are connected. So either I can do E plus E plus E, that is 3E. Or I can simply do NE, which is 3E. In both the cases, you will get the answer. But if the values are larger, then we have to abide by the laws. That is NE you will calculate. R equivalent will remain the same. R plus R1 plus R2 plus R3. This is how we calculate when we have series and parallel combination, right? So here also what we will do, we have series and parallel combination here also. But in series, if you're adding R1 plus R2, all R are having the same values. We have taken identical cells, so their internal resistances are also equal and their EMFs are also equal. So when you add all the internal resistances, you get the same value. See, this will be also equal to R plus R plus R up till all the values of R. So this is equal to NR. This is equal to NR. Fine, keep on adding all the values of EMF, add all the values of internal resistance. But if you have this external resistor in your circuit, if external resistor is present in your circuit, external resistance, we have taken it as R. So now see, earlier when we discussed the terminal potential difference, the EMF question, all these portions, when we discussed them, what did we notice? When we had V is equal to IR, that time E was just E, R was just R plus small r. But do we have the same thing right now? No. See, now your currents formula, this will become, what is the potential now? After the combination, your potential now is NE. This is the potential. So this becomes NE this time, divided by what you have as the external resistance, that remains plus R. But what is the internal resistance now? Small n into R. This is the formula that we have obtained. This is the formula that you are going to use. What is meant by every term in this? See, I is current making. We have I as the current. N is the number of cells you have. The number of cells is the value of N. N is the number of cells we have. E is the EMF, and EMF is same for all the cells. R, this is the external resistance. External resistance. And small r is the internal resistance. Before we move on to the detailed cases, you can note it down. First note down these, then we'll see two cases in every case, parallel also in series also, and that comes in your exam. Note down
Ma'am,
this. Yes, say.
and your external resistance will be same.
See, external resistance is the way you calculate external resistance. External resistance we have already studied. That's why I'm not taking this. This is actually your R equivalent. How do you calculate external resistors in series? R1 plus R2 plus R3. So that is the same. But we are not talking about external resistors because that are not identical. Your cells are identical. If your cells are identical, that means EMF is E, internal resistance is R. That is same everywhere. Regarding external resistor, that we have studied in detail, series and parallel and everything, that you will apply here if more than a single resistor is given. All right, that's why I've just kept it as R. This is actually your R equivalent. You can mention this as R equivalent also. This is your R equivalent. Clear, Chavez?
Yes.
See class, now you can get two cases. One is when your external resistor's value is greater than your internal resistance value. And second is when other thing can happen, when your internal resistance value is greater than your external resistor. Now see what difference come if your external resistor, which you have considered in your circuit, is very much greater than the internal resistance. So we can conclude this with the help of formula. Look here, the formula over here is I is equal to NE divided by R plus R. This time, if I am saying capital R is greater than small r, this term is very huge. This is very huge term. And this is a small term. For example, if I tell you value of external resistor is 10,000 ohm and value of internal resistance is 1 ohm. And I ask you the denominator, what your answer will be? When you will write R plus R, means when you will add them. So this will be equal to 10,001. So will you ever use 10,001 in your calculations, or you will still prefer it as 10,000 only? Because capital R's value is so huge that if you add 1 ohm resistor or a very small value, let's say 25, 35, and capital R is greater, thousands, 2,000, 3,000, 10,000, then the significance of small r decreases. So see, here it's like you're adding into a very big quantity, you're adding a very small quantity. So R plus NR, this almost becomes equal to this R only, to this greater than, this gets neglected, right? If 1,000 plus 1 you are doing, so you write your answer as 1,000 only. You don't change your or modify your answer. So that is R plus NR is almost equal to R only. Now see, in this formula, if I put this term as capital R, because I am seeing this condition, no, if this is very greater, this is very much greater, so this shouldn't be written. So what the formula will now become? Formula of current becomes NE divided by capital R. Now you can notice, okay, I'll tell you one thing. Let us do the parallel one first, then you will notice something. Now, if small r is very much greater than capital R, then opposite will happen. See, R plus NR will now almost be equal to NR, because now your NR is so huge and the external resistor, let's say only one external resistor is connected with just 2 ohm value, and all the summation of all the internal resistances when added together, they are becoming something, let's say 10,000, 1,000, 3,000 like this. So in this, if you're adding a very, very small number like this, for the external resistance is so small, so external resistance will now be neglected. So what is the conclusion now? I is equal to, this was NE. Instead of R plus NR, we will just write NR, right? So NN gets cancelled. I is equal to E divided by R. Now look, E by R, this is just E by R, and this is N times E by R. Which is greater, first case or second case according to you?
First case.
First case, very good. This is first case, because this is N times something and this is just something. You are having something over here, this is N times something, so this will be greater. So that's why in series combination, when you're, because these types of questions, they come in your numericals also, and they can come in your writing theory questions also, in your conceptual questions. See, when your external resistor is greater than internal resistance, then we get the maximum current. And that's why whenever we have external resistance greater than internal resistance, we prefer series combination. This will get clear. Let us do parallel combination, then that will see. I'll explain the point again. But just remember this, in this case, we are getting the maximum value of current. So when do you get the minimum value in series combination? When do you get the maximum value? You have to remember that theoretically also, and formula wise also. We will practice a question. So by that it would be clear how to solve these types of questions. Note it down, then we'll discuss parallel combination. Look here, now we have parallel connection. So to differentiate between the number of cells that are connected in series and number of cells that are connected in parallel, I'll use the letter M, right? M number of cells are connected in parallel. So that when we have the combination of the formulas, you understand that when I'm referring to M, this means all the cells connected in parallel, and N means number of cells connected in series. Now, when the cells are connected in parallel, can anyone of you tell me what should be the equivalent EMF? Equivalent EMF. NE I have told you in the series part. Yes, Rabba?
Same.
Shave says same means?
Even E plus E plus is like voltage remains same,
Okay,
right, in
NE,
parallel.
you're saying same as series. Okay. NE, Tharif is also saying NE. Any other answer? Rabba, you're answering something?
Any only.
NE, NE. Okay, yes, Austin, your answer? Shahid is absent today. Very good, Austin. C class, they are connected in parallel combination. Voltages will remain the same. Even if you take equivalent voltages throughout the parallel connection. We have studied, no, whatever is the total voltage, that is only there in every branch. That's why equivalent EMF will become E. Fine. So this is the difference that comes. And can anyone answer about the equivalent internal resistance? That is same as you calculate for external resistor. That means 1 by R equivalent, not R, C, not R, because they are connected, proper parallel connection is there. So this becomes 1 by R plus 1 by R plus 1 by R till all the values of them. So finally, what do you have? You have M by R. Like if you have 5 cells of 1 ohm, so what will you write? 5 by 1, that's how we write. So this is M by R. So R equivalent will become R divided by M. This will be the value of equivalent resistance which you will obtain. So this time you will divide for equivalent resistance. Now coming to the conclusion of the formula. So current's formula. Now what is your potential? Let's say M number of cells are present. Equivalent EMF throughout the circuit is E. But let's say M number of cells are present in it. So for every cell we have taken, for every, this is actually C. For equivalent EMF is E, so this becomes E divided by. What is the value of external resistance? This I've already told you. We take it as R, whatever R equivalent comes. And what is the value of internal resistance? R by M. So what do we get? If you take the LCM here, this becomes M here, MR plus R with E. So this M can go up. Final formula will become ME divided by MR plus small. This is the formula which we will get. Again, here also you will have two cases where your external resistor is greater than internal resistance and your internal resistance is greater than your external resistor. See, if external resistor is greater, so MR plus R, this should almost be equal to the bigger term. That's what we take. So this is almost equal to MR because this is a very small term. So we neglect it and we write it as MR. So what does the formula become now? ME divided by MR. MM gets cancelled. We get E divided by R. And if you have small r greater than capital R, means your internal resistance. If your internal resistance is very much greater than your external resistance, then what we will do? MR plus small r, this is almost equal to your R. So formula of current becomes ME divided by small r. That's it. Now see, which current is maximum? Is the first current still maximum? First or second? Maximum current. In which case, first or second?
Second, ma'am.
Second case. Very good, all of you. So this time you get the maximum current. Now, one very important conclusion, because in your questions, this won't be specified. When do you have to choose parallel? You will be just getting the values without the circuit diagram. So you won't understand whether you have to choose series combination or you have to choose parallel combination. C class, if your internal resistance is greater than external resistor, let us look at both the cases. Case 1, capital R greater than small r, external resistor greater than internal resistor. We got the maximum current here. And in parallel, in the first case, we didn't get the maximum current. So if your external resistor is greater, which you will prefer, series or parallel? Look here, class. See, this is the first case from here, parallel combination. Capital R is greater than small r. Here you are getting minimum value of current in parallel. And in series combination, in the first case, you are getting maximum current. So if you have external resistor greater than internal resistance, means case 1 if you have. So would you go to series prefer or would you prefer parallel combination?
Series.
Series, very good, Rabba. Because see, if you are getting maximum value of current in the first part by connecting them in series, why would you connect them in parallel, divide the current, get your current reduced? Suppose I have connected bulbs. So would I like or would I prefer that the connection should be the current should be very low, voltage should be very low, the bulbs should glow dim, they shouldn't glow brightly. No, we want more current. That is what is the whole purpose of this lesson. How to get more current. So in the first case, it means wherever you are encountering in your calculations, in your numericals, because why I'm telling you this? Because sometimes it becomes very difficult how to identify. So if your external resistor becomes greater than, this is how you can prefer. So in this case, series combination is chosen. Whereas if you see in the second case, in series, we are not getting the maximum current. So we won't prefer this while we are getting the maximum current here. So now parallel connection is chosen or preferred. This is how this will help your numericals also. We'll practice one numerical from this part. But before that, note down from here.
Finish.
We are not taking m by r because see 1 by r equivalent is coming m by r. Do we need 1 by r equivalent or r equivalent? We require r equivalent. So for r equivalent, we have to reciprocate it.
Okay, scroll down.
In both the cases, in which case you are answering, Rabba? You have two cases. See, 8 identical cells of EMF 2 volt each and internal resistance 1 ohm are connected to. See, you have internal resistance fixed, you have EMF fixed, number of cells are also fixed. What is different is values of external resistor. Now, depending upon the values of external resistors, you will get the different answer. In second case, yes, right. Then your answer is right. See, let me discuss. In the first part, resistance is given as 0.05 ohms. Your internal resistance is given as 1 ohm. Class, is your external resistance bigger or your internal resistance? Yes, Humam. Which is greater, capital R or small r, Humamuddin?
Ma'am, can you
Yes,
show the
Tariq.
question again?
Yes, Rabba?
Can you show the question? I didn't complete it.
What small? Small r is greater or lesser? What are you saying? Small r means, what is small r? Internal resistance or external resistance? Is small r internal resistance or external resistance? Yes, Humam? Yes, Tariq. Right. We will use that. Yes, Humam, small r, you are saying small r is greater than capital R. What is small r? What is capital R?
R is external.
Capital R is external,
Yeah,
small
capital
r
R, yes,
is
yes.
internal. All right. Now, yes. So, see, if your capital R is lesser, means small r is very much greater than capital R. What did we study? When small r is greater than capital R, we prefer parallel connection. So, if we are preferring parallel connection, in this, we will prefer here, we will prefer parallel connection because small r is greater than capital R.
Ma'am,
Yes.
can you scroll up? I was disconnected.
Who is this?
Chavez answer.
Okay, Chavez. I'll show you the question. Fine. Now we will prefer parallel formula. So what was the parallel formula? ME divided
Yes,
by
I can
M.
scroll more.
Yes.
Scroll more.
You're telling the answer?
No, no. Can you scroll more?
Okay. Before the question you have written, Chavez?
Case 1 and case 2, I'll take screenshot.
Question you have written, no?
No, case 1 and case 2, I have to take screenshot.
These you have written?
Yes.
And what about the question? Okay, let me have the question like this, meanwhile. So internal resistance is small r. Now value of M, number of cells are 8. So we can say 8 into what is the EMF? EMF is 2 volt. Divided by M is again 8. External resistance is 0.05 plus what is internal resistance? 1. So 16, this becomes 16. This is 4, 5, so 11.42 ampere. This should be the answer. Please check it once by your calculations also, once you're doing it. Second case, B part says that external resistance value is 100 ohm. Internal resistance value is 1 ohm. Now you can easily see capital R is very much greater than small r, right? 100 is very much greater than 1. So here we prefer series combination. And what is the formula for series combination? NE divided by R plus small nr. And number of cells, n is equal to 8. So I is equal to 8 into 2 divided by 100 plus 8 into 1. So this becomes 0.148 amperes. This is the answer for the second part. Note down the question and then note down the solution. Yes, B, not B, R, this is 100. Yes, 100 plus 8 into 1. So 108. 16 by 108 should come around this. Check, cross check. If there is any error, let me know. Now, look class, if you have series combination, right? Number of cells are connected like this. We have added them in series. If I take such combinations and I add them in parallel, like this, individually, all the series combination, I have added them in parallel. So whether I'll choose the formula of series connection now or I'll choose the formula of parallel connection now. So look here, you can look here, this part. They are connected in series.
And your voice is lagging. Your voice is lagging. Your voice is lagging.
Your voice isn't audible.
Your voice is cracking, ma'am.
My voice is cracking. Isn't it clear? Just wait. Yes, class. Is it fine or is it still breaking?
Fine, ma'am.
Okay. I was saying if we have series combination together and then I have connected them in parallel, right? I had series combination and I have connected them in parallel also. So I have mixed grouping now. Series is also present and parallel combination is present. So which case do we prefer? See, if we go by this appears in series, means E equivalent will become NE and R equivalent will become NR. This is what we can do, right? So if this is the number, if let's say I have taken their equivalent resistance, let me take their equivalent resistance. If I take their this row's equivalent resistance, still it's lagging. Others? Austin, Faiza, my voice is audible to you. Tharif, Rabia. It's fine, no? I think, okay. I think Shavez, it must be your internet because others are able to hear. And my also Wi-Fi is fine. If others are also having an issue, then you can text in between. I'll check the connection again. Shavez, just check your connection first. See, I have taken them. All the cells are connected in series. Let me find the first row's equivalent resistance. Let's say this is the cell. Now its EMF will become NE, its resistance will become NR. Its resistance will become NR. Fine. What about this row? This will also become NR and NE. What about this row? This will also become NR and NE, right? And now their resultant, this I have connected them in parallel. They all have been connected in parallel to this. Now see, we have at least simplified. This fact has been simplified. Look here. They are connected in parallel. Here you are having M number of rows and N number of cells are present in each row. Let's say these number of rows, 1, 2, 3, 4, 5, these are M. M number of rows you are having, right? Because see, if you directly solve it, from where will you start? You have to have a proper starting point, no? How you will solve the circuit. So see here, when we have all these cells connected together, we found their equivalent resistance of first row, then equivalent resistance of second row, equivalent resistance of third row. So for each row, equivalent EMF will be NE and equivalent internal resistance will be NR, right? So when I have connected all of them in parallel, for me now this circuit, I have reduced this circuit to this. The way in our series and parallel questions, what do? We start with a series and parallel question, then we start first series, then which are parallel, then which are in series, like this. So same way, whichever were in series, I have concluded them into their form. Now I have to find out the parallel connection of these. So what do we study? EMF will remain the same. Now this is your circuit. No more you have this circuit. Your circuit is this one, right? So your parallel connection equivalent EMF, this will still be NE. Why not E this time? Because E was when you had only one column. Now you are having so many columns, so many rows you are having. This is your circuit. If every cell is having potential NE, so it will remain the same because this is parallel connection. Otherwise, we would have multiplied it to M. Why aren't we multiplying this to M? Because potential remains same. If every cell is having potential NE, equivalent EMF will be NE. Coming to internal resistance, so 1 by R equivalent will be 1 by NR plus 1 by NR up till M number of times by NR. So what you can conclude, this is M by NR, means NR is for individual cells, but when you add them in parallel combination, what is the value of R equivalent that we get? NR divided by M. Final formula of current, if you have mixed grouping, I is equal to NE divided by resistances are whatever equivalent resistance you get through series and parallel combination. R equivalent is NR by M. So again, NE is there, R plus NR is there. Take the LCM. This will get multiplied, M will go up. Final formula, MNE divided by MR plus NR. A very important formula because you have many questions from this. Diagram won't be given to you. This figure won't be given to you, just the values like this. In this question, no figure was given, but you were able to solve it with just a help of values. Right. So here I've written also, yes. See, this is a condition when we say maximum power transfer of power. Maximum power transfer, we call this condition when your NR becomes almost equal to MR, means this and this, they become comparable to each other. In that case, you get the maximum value of current. So M is the number of rows, N is the number of cells. Current is maximum if NR is almost equal to MR. It's NR, not NR. Oh, sorry, yes. Right. This is small r. Thank you, yes, this is small r here. M will all, the best way to remember this is, remember, see, when you had only series connection, then you had N here, N here. When you had parallel connection, M was here, M was here. When you have mixed connection, both MN will come here and M was already with this and N was already with this, means everything gets combined together. And remember this condition because this condition has been asked. This condition NR is almost equal to MR. Quickly note down all these points regarding mixed grouping. Questions on mixed grouping can also be asked to you.
Ma'am, can you do little up? I done, ma'am. Do it.
Yes, classy, this power heating effect of current, this will come in detail in your AC also, but in your DC circuit, for your DC, before we move on to AC, I have discussed this, but I just want to brief you with this so that you at least have everything written all together, right? See, heating effect of current, just discuss this and you can write down everything together. Heating effect of current. When we talk about power, power is actually heat per unit time, heat dissipated per unit time. So whenever we have to calculate heat, you can calculate it as power multiplied by time. These are just basics, you all know, we have already discussed. I just want everything should be written all together in your notes as well. So formula of power is, in terms of current, is I square R. In terms of voltages, V square by R. And without resistance, with just current and voltage, we write power as VI. This will be used, all these will be used in AC also, in alternating current also. But regarding direct current, when we are talking about direct current, that time also you should have the idea. One more formula of heat is H is equal to I square RT, means power into time. See, you can see this is power and this is time. One last thing, SI, unit of power, is what? So we write this with the help of capital letter W. That completes your current electricity. Note down all these points. I think you were here, no? Yes, Austin, the lesson is completed. If you people have written, all those who have written, you can start leaving. Those who are writing, you can stay. You don't have your after class assessment today. So you can easily note it down and you can leave if you are done. That we'll start with magnetics now in the next class.
Ma'am, can you do little up?
Yes. Okay, Faiza, thank you.
This case for